Hello and thank you for watching my video. My name is Astrid Krasniqi. I'm CCNA and CCNP certified instructor. On this video we are covering CCNA Semester 2 Routing and Switching Essentials. This is Chapter 8, Single Area OSPF. Chapter 8 is divided in 3 sections. We have Section 8.1, Characteristics of OSPF, then Section 8.2, Configure Single Area OSPF, and then Section 8.3, Configure Single Area OSPF version 3. Section 8.1, Characteristics of OSPF. Upon completion of this section, you should be able to explain the process by which link state routers learn about other networks, describe the types of packets used by Cisco IOS routers to establish and maintain an OSPF network, and then explain how Cisco IOS routers achieve convergence in OSPF network. Evolution of OSPF. OSPF is a link state routing protocol. That means it keeps in the memory the whole topology of the area. OSPF was developed, version 2 was developed in 1988, and that was for IPv4. OSPF version 3 was developed in 1989 and updated in 2008. They included support for IPv6. OSPF version 3 does support IPv4 and IPv6. OSPF version 1 was never released. It was the only experimental routing protocol and never deployed. So we have OSPF version 2, released 1988. This is for IPv4. And OSPF version 3, released 1989, updated in 2008, and this is for IPv6. You really don't need to remember the dates as far as the exam is concerned, when were they released. You just need to know there's 2 versions, version 2 and version 3. Version 3 supports IPv4 and IPv6, while version 1 was never released. So OSPF is classless. It is classless by design. Therefore, it does support a VLSM, or variable length subnet mask, or CIDR, classless interdomain routing. It does send a subnet mask with updates, routing updates. OSPF is a link state routing protocol. Like we said, it's interior gateway routing protocol. So if I just mark it here, these are our interior gateway routing protocols. And we have exterior gateway routing protocols down here. But exterior gateway routing protocols is only one BGP. So interior gateway routing protocols, we have a link state routing protocols. And that's OSPF version 2 and version 3. So it uses areas for scalability. So if OSPF can scale, so it works very good in small networks as well as in large networks. And if we need to scale to large networks, then we use areas. So these are some of the features of OSPF. Like we said, it's a classless by design. That it does send the subnet mask with routing updates, and it's very efficient. So router changes triggered updates. It sends a triggered update every time there's a change on the routing table. So it's different to RIP, for example. RIP does send updates every 30 seconds, even if there's nothing has changed. While OSPF waits until there is a change. It uses the shortest path first algorithm to choose the best path. OSPF has a fast convergence, so as soon as there's a change, you notify the neighbors. The neighbors, before they even run their own algorithm, they notify their own neighbors, and so on. So right away, very quickly, all the neighbors they find out about the change, and then they can start running their routing updates through running their own algorithm. It's scalable, like we said. It works very well in the small networks and large networks, and it's secure. Well, by default, it's not secure, so it doesn't have any authentication or so on. But we can enable message digest 5 authentication, which you authenticate the updates where you get it from. You authenticate the neighbor. OSPF data structures. By default, OSPF routing protocol keeps 3 tables. Keeps adjacency tables. This is who is your neighbors. Keeps link state database. This is what your neighbors are telling you. And keeps a forwarding database, which is the best path to the destination. You put it on the routing table. So the first table is called adjacency table or adjacency database. This is the neighbor table. So in there, you will see all the routers, all the neighbors that you have the bidirectional communication, or you establish the adjacency with. This table is unique for each router because router 1, maybe the neighbors router 1 is router 2, 3, and 4. Maybe router 2 has got only neighbor for router 1. So obviously this is going to be a unique for each router. And this table, we can run it with a show IP OSPF neighbor. We can see it. The next table is that we keep is topology table. And this is what your neighbors are telling you, what networks they are advertising it to you. In OSPF terms, this is called link state database, and lists information about all other routers in the networks. This database shows the network topology. All routers within area have identical LSDB. So it has to be identical. So the command to view it, show IP OSPF database. And like we said, the third table is a routing table. And in OSPF terms, we know this as a forwarding database. And here we have the list of routes generated when an algorithm is run on the link state database. Each router's routing table is unique and contain information on how and where to send the packets to other routers. This can be viewed with the show IP route command, and we can see what they are OSPF routes. So for example, it's going to be unique because to every destination, you run the algorithm and you find out the fastest way to get to the destination. And it's going to be unique on every router. This is a OSPF Routers Exchange Packets. These packets are used to discover the neighbors' routers and also to exchange routing information and to maintain accurate information about their networks. So we have 5 packet types in OSPF. We're going to go in more detail later on, but for now, the first packet type is hello packet. This packet is used to establish the neighbors, to discover the neighbors first, and establish adjacency, right? After we agree on some attributes, then we establish the adjacency. When we have the adjacency, then we start exchanging our database. So we tell the neighbors what we know, and they tell us all the destinations they know. Now the database that we're exchanging is just like it's not a full-fledged how to get to the destination, right? It's just like a small index on every destination you know. Now, if I know about every destination that you know, great. We both know the same information. We have to have the information identical, so we both have to know the same information. But for some reason that you tell me of a destination that I don't know about it, then I'm going to ask you by sending you a link state request saying, okay, you just told me about destination XYZ. Can you please, I don't know about that destination, please tell me everything there is to know about there. So that's a link state request. And the fourth packet type is link state update, when you turn around and say, okay, well, here's the information about that destination that I told you. The last packet type is link state acknowledgement, and OSPF is reliable and unreliable. So reliable, some of the packets can support reliable packet delivery. So database descriptor is a reliable packet, link state request is a reliable packet, and link state update is reliable packet. So link state operation, first we send the hello packets and to discover our neighbors. If a neighbor is present and OSPF enabled router attempts to establish a neighbor adjacency with that neighbor. So if we find, okay, there's a neighbor out there and we try and establish adjacency with that neighbor by exchanging our hello packets. Link state advertisement, or LSA for short, that contains the state and cost of each directly connected link. So for example, when we establish a neighbor adjacency with our neighbors, then we send them a link state advertisement. Link state advertisement, they will contain all the cost and state of each directly connected link. Routers, they do flood these LSAs to adjacent neighbors. Adjacent neighbor receive the LSA, immediately flood the LSA to other directly connected neighbors until all routers in the area have the LSA. So for example, if I grab this network here, router 1, and it sends it to his neighbor, they sends it as LSA. LSA, the neighbor on R2, will take this LSA and immediately will flood this LSA. So without running the algorithm or anything, it sends it to his neighbors. And then the neighbor sends it to his neighbor sends it to his neighbor, and so on. So this LSA, it will travel immediately to all neighbors. So until all routers within the area have all the LSAs. So after we have exchanged our LSAs, then we build the topology table. The topology table based on the received LSA. So we build this table to say, okay, well, router 1 has got this LSA here. Router 1 has received LSA about this router, about this network, and so on. All these LSAs, they go to this router. And say this network, they all go to router 1. Now router 1 puts that on the database, puts in the database. And then, for example, if you received about destination about many different paths, so for example, to this destination here, router 1 can go through router 2, it can go through router 4 to get to the destination. It will run the algorithm, it will find out the best path to get to the destination, and it will pick the best path and it puts it on the routing table after has run the algorithm. From the shortest path first tree, the best paths are inserted into the routing table. So just to recap, what do we do here? We exchange our LSAs, so we update all LSAs to every router. We'll send it to the neighbor will flood it to their neighbors, the LSA tells the cost of directly connected at the link and the state of that directly connected link. Then we put all the LSAs that we receive, we put them on our database, and then we run the algorithm, Dijkstra algorithm, to find the best path to the destination. Once we found the shortest path first, then we take that and we put it on our routing table. So this is what happens on a link state operation. We have a single area and multi-area OSPF. If we have one area, only one area, that's area 0. This is our backbone area. So everything starts with area 0. All routers, single area OSPF is useful in smaller networks and with a few routers. Multi-area OSPF, implemented using a two-layered hierarchy, all areas must connect to the backbone area. So we start with OSPF is area 0, and all other areas, they connect to the area 0. Area 0, we really don't connect any PCs to it, or desktop computers, or for example printers, servers, or whatever. We don't connect them to area 0. So area 0 is really just there as a transit area. There's another name for it, a transit area, because all the communication between the areas has to go through area 0. This is a loop prevention. So there's no way, not allowed, communication to happen from one area to another area without going through area 0. Right? So with OSPF, there's no communication between the two areas allowed without going through area 0. Area 0, interconnecting routers. So the router that connects two areas together, areas 1 in this case and area 0, this router, router 1, this is called ABR, area border router. Like the name says, because it's connecting two areas, there's an area border router. It's useful in large network deployment to reduce processing and memory overhead. Link failures happening in one area is localized only, so affects only local area. So for example, if there's a failure here in area 51, we have a failure here. Now all that failure, instead of everybody running the algorithm and exchanging the LSAs about that link, the state of that link, it only affects area 51. The area border router, in this case router 2, will isolate the fault to area 51 only. Routers in area 0 and 1 do not need to run the shortest path first algorithm. So this is the encapsulating OSPF messages. So first, we talked about, which we're going to talk even more, the OSPF packet types. The first packet type was a hello packet. This is how we meet our neighbors. The second is database description. So we describe our database, very small index information to what we know, where to go to. And then if the neighbor doesn't know about some destination that we know, they send a link state request. Then we update them, we send the link state updates, and then those three in the middle, they do get acknowledged. Now, OSPF header, OSPF packet header has a type. What kind of the packet is it? Hello, database, DBD, LSR, LSU, or LSA, or link state, LSAC, I should say. Router ID and area ID. So for example, within the area or router, well, pretty much the whole OSPF, the whole autonomous system of OSPF, you do want the router ID to be unique, right? And two routers, they will not become neighbors if they are not in the same area. So the area ID has to match. For example, if one router is in area 0 and another router is in area 1, they're not going to become neighbors. When we send the updates, the protocol field of OSPF is set to 89. So if you look at the layer 3, you see, okay, well, if you see protocol field to 89, we know that it's OSPF packet. So if you see 88, for example, we would know that it's EIGRP packet. Or if we see protocol field of set to 1, we know it's ICMP packet, and so on. The destination address is typically set to one of two multicast addresses. So we have 224.0.0.5 and 224.0.0.6. So 224.0.0.5, we send it to all OSPF routers. And 224.0.0.6, which we can talk a little bit more very soon, is set to DR and BDR only. So DR and BDR, they listen to this address. And all other routers, they listen to 224.0.0.5. The destination MAC address is also a multicast address. And as you can see on the screen, it's 01005E, and then 000005 and 000006. So these are 5 packet types that we're going to talk in more detail here now. So the first packet type, like we've gone through again and again, is hello. This packet type is used to establish and maintain adjacency. So we meet our neighbors, make sure the neighbors, they are same area, the unique router ID and so on, and then we maintain it. So we keep sending each other hellos to make sure that we know that our neighbor is still there. The next type is a database descriptor packet, which describes the content of OSPF router link state database. Then, if from that description we find out that we don't know about some destination, then we send a link state request a specific piece of neighbor's router's link state database, and then we send an advertisement, a link state update, transport link state advertisement to neighbor's routers. So we send a link state advertisement inside link state update. And then we have a link state acknowledgement, or LSAC. So these 3 packet types, they do get acknowledged. For example, this packet type number 2 gets acknowledged, packet type number 3 and 4, LSU and LSR, they do get acknowledged. So hello packet of OSPF is discover our neighbors, establish the adjacencies, and maintains the adjacencies, just not to leave it. Advertises parameters on which 2 routers must agree to become neighbors. So the hello interval, we have to agree on that. So if I send to you every 10 seconds hello, you have to send me every 10 seconds hello. Otherwise, we're not going to become neighbors. And then dead interval. So how long do I have to wait if I'm not getting hellos from you? So for example, if we say you're going to send me every 10 seconds, now how many seconds it has to pass before I declare my neighbor as down? And the network type, are we like a point-to-point or point-to-multi-point? So what is our network type? We have to agree on. And area ID as well. It has to agree, it has to match on the area ID, otherwise we don't have neighbors. So elect the designated router and backup designated router on multi-access networks such as Ethernet and frame relay. So if we, for example, establish neighbors with our in our multi-access network, then we have to elect the DR and BDR. So first is a type. Okay, on the top there you can see is type 1. Type 1 is matches to hello. So this is a hello packet. Type 2, if it was, will be DBD. Type 3 LSR. Type 4 LSU, and then LSAC. Type 5. The next section is router ID. So not to go too fast. So this is ID of the originating router. So this has to be unique within the area. Then we look at the area ID, areas from which the packet has been originated. Then we look at the network mask. It's a subnet mask associated with the sending interface. Then we have a hello interval, number of seconds between the sending routers hellos, and we have the dead interval. So down here it doesn't show, but it's router dead interval. So how long we have to wait before we declare the neighbor down. Router priority, this is used for the DR and BDR election. So we're going to talk a little bit more about that very soon. But by default, router priority is 1. And if the router priority is all set to 1, so we have to look at the router ID to elect the DR and BDR. If router priority is set to 0, that means I don't want to take part in the election. Then we have a DR, router ID of the DR, and BDR, router ID of BDR. And last is we have the list of the neighbors. So list of OSPF router ID of the neighboring router. So for example, if you hear a hello message from a router, right, you take the router ID and you put it on your list of neighbors. Hello packet intervals. So the OSPF hello packets are transmitted to 224.0.0.5 in IPv4 and FF02::5 in IPv6 for all OSPF routers. These packets are every 10 seconds this is default on multi-access and point-to-point networks, or every 30 seconds. This is a default on non-broadcast multi-access network. Dead interval is the period that router waits to receive the hello packets before declaring the neighbor down. Router floods the link state database with information about down neighbors out of all OSPF enabled interfaces. So for example, if we say that one neighbor just told you about 50 destinations, and if he hasn't sent you hellos in so many seconds, you're going to declare that neighbor down, as well as you're going to remove all the packets, all the information that neighbor has told you. The dead interval on a Cisco routers by default is 4 times of hello interval. So 40 seconds for in a multi-access network and point-to-point, and 120 seconds on a non-broadcast multi-access network. So these are in the fourth packet type is link state update. Yeah, in link state update, when you think about it, is like an envelope, and in that link state update, there can be the link state advertisement. Now, link state advertisement, these are the different type of link state advertisement. For CCNA 2, you don't really know in depth. We go in more depth in CCNA 3 about different type of link state advertisement. So operation states, when an OSPF router is initially connected to a network, it will attempt to create adjacency with the neighbors, then exchange routing information, so exchange a database, and then after exchange, it builds its own database, and then it's going to run the algorithm to try and find out the best route. Then it will reach the convergence. Well, before we do that, they has to go through some states while attempting to reach the convergence. So first state is down. Down state is we haven't really started the OSPF. As soon as we start the OSPF and we send in OSPF packets, we are still in down state. We're going to transition to initializing state very soon. When we receive a hello packet from a neighbor, but on their neighbor list, we are not there, then we are in initializing state. We are not going to move to two-way state until we see our router ID on their neighbor list. For example, if I go back, let me just go back here for a second. If I go back here, if I get this hello packet and from the neighbor, and I don't see my router ID here in list of their neighbors, then I can't move to the two-way state until they put my router ID on their list of their neighbors. When I see that, then I transition from the initializing state into two-way. So if I go back here, we got to two-way state, right? So when they see their router ID in our hello, in our neighbor list of the neighbors, then they will move to a two-way state, and then we can move on to the synchronization. So that's the first bit, is to establish our neighbors adjacencies. So synchronization, then we move on to X start state, where we here, for example, if we are in multi-access network, we elect the DR, designated router, and backup designated router, and we find out who's the slave and who's the master on a point-to-point, for example, who's going to start the exchange. And then we actually exchange it. So the master starts with sending the link state database, and then the slave, if there's some link that he doesn't know about it, he will send a link state request, and then he's going to send a link state update. And when they all have the synchronized, it will be loading state. We have a database synchronized, and then we run the algorithm, shortest path first algorithm, OSPF DR and BDR election, for example, like we said earlier, so if there's a new link here, this LSA here, this router is going to grab this LSA and it's going to send it to all the neighbors. Now the neighbors, what is the job for the neighbor to do? The first thing is they're going to flood that LSA to their neighbors, and their neighbors, they're going to flood it to their neighbors, and we have quite a lot of LSAs just from one new link here, new link state advertisement. So the best way to do is to elect a designated router, a DR, and then all the LSAs are going to go to the DR, and it's the job of the DR to forward that LSAs to non-DRs. So I'm going to try and write on this. It's not very good, but I'm going to try and write it. To elect the DR, we look at the priority first. Yeah, so priority, that's the first one. Now by default, all the priority is 1. So all the routers, the priority is, you can see this is a multi-access network. Yeah, so priority of 1. Here, here, here. If this router has a priority, for example, of 0, that means no election. I don't want to take part of the election. So do whatever you want. I don't want to be DR or BDR. If priority is the same, the next thing we need to look at is router ID. Router ID. The highest will win. So if I put an arrow here, the highest will win. So imagine this is 1.1.1.1. This is 2.2.2.2. This is 3.3.3.3. And this is 4.4.4.4. Now this, because it got highest router ID, will become the DR, right? And here, this one, it will be the BDR. It doesn't matter what the router's ID is, this one here, because it's not taking part of the election anyway. So the DR and BDR will listen to a different address, 224, if I can write it here, .0.0.6, a different address to other OSPF routers. So this now LSA, instead of sending it to all the routers, the router 1 here will take this LSA and it will forward it to the DR. The BDR will get that as well, yeah? And this D is the job of the DR, take that LSA, take the LSA it's got, and it's forwarded to non-DR, or they call DR others. DR others, they listen to 224.0.0.5. Okay, thank you very much for watching this section, 8.1, characteristics of OSPF. Please have a look at my other videos and don't forget to subscribe. This has been Asir Krasniqi, and hopefully to see you in the next video, 8.2, configuring single area OSPF. Bye bye.